It's my great pleasure to introduce Professor Abishek Gupta from the University of Washington, where he's leading the Weird Lab, right?
Yes.
And yeah, he focuses on foundation models for robotics and reinforcement learning. And we're super excited to hear from his amazing work with today's topic, simulation for robotic manipulation without the pain. So yeah, the stage is yours, Abishek.
Awesome. Thank you, Oier. Thanks for the kind invite. And I'm looking forward to talking to you all a bit about some of the work we've been working on around simulation for robotics. So as Oier kind of alluded to, my group is called the Weird Lab, the Washington Embodied Intelligence and Robotics Development Lab. And they told me it is okay, so this is the name we chose. And so these are a lot of my students. They're the ones who did all the work, and so I just wanted to highlight them up front. Okay, so the goal of our group in general at Broad is to deploy robots into messy, unstructured environments, right? So I'm generally a lazy person. I don't like to do any work. And I want my robots to all do, right? So if I have a kid's playroom, I want all of it to be cleaned up by a robot. If I have, my kitchen doesn't look this clean, but if it was, I'd like it to be cleaned up by a robot, right? So I want to think about settings which are messy, unstructured, unexpected, right? And so you can't use the classical paradigm of sense, plan, act, which has been used in robotics for the last 50, 60 years. And so you know, the fundamental premise of what we think about is robot learning, right? And so we typically have this sense, plan, act paradigm in robotics, right? So you start by sensing the world, doing state estimation, then think about doing planning, which is like modeling, and then control or planning, and then finally you execute things on the robot with a low-level controller. And so this is the typical sense, plan, act paradigm. But for every domain, you have to do a bunch of engineering, you have to do a bunch of cost engineering, you have to do a bunch of model engineering, right, or primitive engineering. And the fundamental theme I'm going to kind of keep going back to is I'm super lazy. This is my lazy potato. This is a metaphor for me. I'm like very lazy, and I want to do this without the effort of having to design controllers and algorithms per domain, right? And so that kind of took us from robotics 1.0, which is the sense, plan, act paradigm, to robotics 2.0, right, which is what you'd often refer to as end-to-end learning or robot learning or data-driven robot learning, right? And the idea being you kind of remove a lot of those components and go from perception to control. And so you go from like your input sensors out to controls that you can run on your robot, right? And typically you'll represent this with a big neural network that you will train with lots and lots and lots of data. And so this sounds like a great principle, right? Like it's worked so well for us in other domains of life, but in robotics, it's not going to be that simple to actualize. And so a lot of this talk is going to be about how to actualize the principle of end-to-end robot learning. Also, if anyone has any questions, please interrupt me. Happy to stop. Okay, so maybe to understand what it takes to actualize robot learning with lots of data, it's useful to look at what has happened in other domains, right? So let's look at things like language or vision, right? And you see that there's been this order of magnitude growth from like tiny data sets like MNIST to ImageNet to Lion, or like Twitter sentiments data set, which is a tiny data set, couple tens of thousands, to like Common Crawl, which is trillions of tokens. And there's of course been a growth, but an important thing in that growth is that it's been passive, right? So the growth has not been someone goes out and like manually types in a bunch of sentences. A lot of this has come from the web scale, and that's because people are using the internet anyways, and so this data is going to grow anyways, right? And so the question is, can we do that for robotics? Now, the tricky thing about robotics is that there's not that many robots deployed in real diverse applications, and so there's not like this passive data stream, right? So there's no data that is just coming in because people are using robots anyways. And so a paradigm that's become more popular in recent years is that of teleoperation, right? So you have these interesting teleoperation devices. This one's called the UMI. There's others which are based on VR, right? And so you have these types of ways of collecting data which are better than what we had before, but they're still not passive, right? And so you still have to go into the field and you have to collect all this data and you have to put in all this effort and you have to take your data collection device or your robot to k different environments, and that takes a lot of money and resources and time, right? And so if we had to cover things at the scale that things have been covered for vision and language, then I think this becomes a proposition that I certainly don't have funding for, right? And so what we've been thinking about is, can we use cheaper sources of data that might still be useful, but might be a little lower quality in some ways? So specifically, we've been thinking about the idea of off-domain data, right? So off-domain data, I mean data sets that are relevant to robotics, but are not literally on a robot, right? So for instance, data generated through generative models, data like large-scale video, and specifically the focus of today's discussion will be data from simulation, right? And so an important thing to note up front is that off-domain data is wrong data. It's never going to be as good as your data on a robot collected by some high-quality expert operator, but it can still be useful, right? And today we're going to try and think about specifically about simulation and whether simulation data can be made useful for robots. Right? So why simulation? Right? Simulation, people are pouring billions of dollars into simulation, and simulation has some fundamental advantages, right? So, for instance, the data is a lot cheaper in principle because you're spending compute on it, not actual man hours. You have privileged information, you know where everything is, you know where the forces are. You have simple resets, and because you know where everything is, you might be able to define rewards easily. And you can go much faster than real time, right? You can leverage all the advantages of largely parallel computation. And that's led to a lot of the advances that are coming in, for instance, humanoids or legged robots. A lot of them out of ETH, right, are coming because of these advantages of simulation. But I want to highlight a specific term here, a specific term of it's only cheaper data in principle. And when you actually get down to the brass tacks of trying to get simulation to work for robots, especially robot manipulation, there's a lot of hidden cost. And today we're going to try and tackle some of that hidden cost. So what is this hidden cost, right? So when I think about, I want to put a robot into an environment, I want to use simulation to, let's say, generate data or to simplify this robot learning process. It's not as simple as, me as a human says, give me data in this environment. It's more a process of, you start off with designing and creating an environment. So some artist, often a PhD student or a professional, would go in and create an environment in Blender, right? So they go in and they edit things, they drag things around, they adjust the physics, they adjust the geometries until something looks good, right? And now they have an environment, but that took them many, many, many hours to create. Now when they have an environment, then they need to go actually get robots to do things in that environment, right? So they have to find ways to either collect data in that environment or generate data in that environment. And for difficult contact-rich problems, that is also an endeavor of many, many, many hours. Okay, now you've generated this data, and then you realize, hey, my simulator doesn't quite match the real world. And so simulator doesn't match the real world, then I go and tweak my simulator and fix these parameters, I fix these things, and I identify the system, and only then is the simulator effective in the real world, right? And so remember, I'm a lazy potato, I don't want to do any work, right? And I don't want to do complex engineering per domain. So all of this work that went from the vision of generating data in a domain to actually generating data and using it for a particular domain is way too much for my lazy potato. And I want to find a way to kind of automate these pieces so I can learn with as little effort as possible, right? So simulation gives us the premise of having less cost of data, but it doesn't really account for the effort in actually designing those simulations and getting it to work. And so today we're going to try and remove that effort. Okay. So the three sections we'll talk about really quickly are starting by generating simulation environments from real data, then trying to generate behavior cheaply in those simulations through reinforcement learning, and lastly is adapting to the real world with minimal amounts of effort. So let's get started. So the first thing that we started thinking about is, okay, every time you have to create an environment, we have to spend all of this effort, and a lot of it is manual design, right? And what we wanted to do instead was kind of use some of the advances in generative AI to automatically generate fully articulated interactive simulation scenes from images or videos, right? And so we've been calling this real to sim. But the idea is that a student here goes into the kitchen, grabs a short video of the scene, right? And out comes not just a static mesh, but really a fully interactive kitchen scene, right? So all the objects are movable, the microwaves and the cabinets and the dishwasher. And really you want to be able to interact with that scene fully so that you can do evaluation or data generation or gaming applications with these kinds of environments, right? And so the idea here is that we're not scaling with human effort, you're just scaling with videos or images that you collect in an environment. And the idea here is that you would produce something that is representative of that environment, not just a generic kitchen. So I won't have enough time to go deep into the details here, but the fundamental premise is we use some of the advances in 3D vision, specifically Gaussian splatting, and then use some of the advances in foundation models, specifically grounded SAM and at the time GPT-4, in order to get interaction. Right? So you can think of Gaussian splatting as a way to go from visuals of a scene, so like multi-view images of a scene, so videos, to high fidelity meshes and visuals, right? So you can think of the visuals you see on the left as basically all just coming directly from raw camera capture, right? And so you can reconstruct and get novel views, but the nice part is that you can also get underlying geometries, and the tricky part is tying the visuals to the geometries so that they align. And then once you have this, you can then think, okay, there's these cabinets, you can separate out the cabinets, you can figure out, are they cabinets, are they drawers, are they dishwashers, are they fridges, and then you can try and articulate them, right? So you can put on hinges and joints and so on, and then you kind of go back and forth in the process a few times to get an interactive scene. And what this kind of results in is if you go to a bunch of different kitchens, you apply the same procedure, and you go straight from videos to fully interactive kitchen scenes, right? So this was no effort, it was just compute, right? You go in with a video, and out comes a fully interactive scene that looks just like the scene that you recorded, but it's fully interactive with a physics simulation. So that's pretty cool. And what do we do with this, right? Why do we care? We're roboticists. So the first and simplest thing to do is you can use it for data generation, right? So you want to, for instance, learn to open a drawer, put a cup in it, close the drawer, etc. Now you have a simulation, and you can use all the nice tools we have in simulation to generate data, and we'll talk a bunch about this in the second section. But one point I want to highlight is that simulation offers a really nice tool for evaluation, right? So a big challenge in real-world robots is that it's hard to evaluate. It's hard to know when you're successful or when you're not successful, right? And well, because you have to have a human in the environment running trials over and over and over and over. So every new algorithm you come up with, it's a huge process to actually evaluate. But one of the nice things about these highly photorealistic simulations is that you can just run evaluations directly in simulation, even for controllers that you trained in the real world, right? And so what we kind of did with these tools that we built was we said, hey, we're going to construct these scenes, right? So these scenes are two scenes that we've constructed in simulation. So these look like the real world, but they're actually just scenes in simulation, right? You can see if you want to see it simulation, you can see tiny little artifacts on the arm or on the side over here, but I promise you there's simulation. And once you have that, you can then say, I can take policies or foundation models and things that I trained in the real world and then transfer them back into simulation, right? And so then you can construct evaluation scenes. So these are a few different scenes at University of Washington and Princeton, and we're able to transfer them directly from the real world back into simulation. And because they're hyper-realistic and visually really realistic and the physics is good, you can actually run these policies directly in simulation with high degrees of correlation. And so here we're running these policies from this company, Physical Intelligence. And so they have these policies that were not trained on any simulated data, mostly on real world data, but you can kind of get them from the real world back into simulation so you can run lots and lots and lots of evaluation. And so what's nice about this is that you can then, you want your things to be close to the diagonal, right? So you want, there's these two measures of Pearson correlation and MMRV, which is rank violation. So you want Pearson to be high and rank violation to be low, and you can see that it's pretty well correlated, but not perfect between sim and real. And the important thing is not that you get the behavior exactly to be the same, but really that you can see things that are better in simulation would also be better in the real world, right? And there was no way to get here unless you had hyper-realistic simulation. So when we tried doing this on far less realistic scenes, it worked a lot worse. And so you do have to do a little bit of magic here. So it's not just 0-0 shot. You have to add in a little bit of simulation data into the training mixture, right? But it's like you add a little bit of simulation data, the models adapt to the general idea of simulation, and then you can evaluate it on new problems. Right? But the important thing is that we were able to construct these environments for data generation and evaluation just by taking in videos without like a ton of effort in creating any of the scenes. So it's like it's gone from a several days effort to a several minutes effort. And so if we think about the takeaways here, it's basically that there's no more manual environment design. I'm happy. I don't have to do the work of doing it, and that's good. Step one is done. Okay. So that's first creating environments in simulation without the pain, right? But we are roboticists. We want behavior, right? We want robots that are flipping and jumping and doing manipulation and building things, right? And so we want to actually generate behavior. And to generate behavior, you have to go a step beyond creating the environment, right? So there's lots of different ways to do it, but two of the tools that people often use are human data collection. So someone will hop into like a VR interface or some track glove and then try to control robots to do things, and you can do this in simulation too. Or someone goes in and uses tools like reinforcement learning, but writes down like a fancy reward function, right? So here's a snapshot from one of the reward functions that folks have used, and you can see that it has like a ton of little terms with these random weightings and these like arbitrary designs. And so it's often a pretty painstaking process, right? And me as a lazy potato doesn't want to do that, right? I don't want to go in and collect data, and I don't want to sit and have to design these environments and these reward functions and stuff with reinforcement learning. And so my goal is to find a way to generate really high coverage, robust data in simulation, but without the pain. And so my students, Tyler and Patrick, asked, can we do RL in simulation without the pain? And so they wanted to perform behavior generation, which is physically accurate in simulation, but without demonstrations, without reward design. And they kind of leverage the fact that simulation is not reality, right? So simulation and reality are not the same thing. And specifically, simulation has some privileges that might make your problem of behavior generation easier than the real world, right? So specifically, we have resets, you have privileged information, you have cheap samples, right? And so we're going to use these different privileged informations to make our job easier. Specifically, we're going to focus in on the idea of resets. When I say resets, I mean I can set the simulator to wherever I want, right? I can't teleport the real world to anywhere, but I can teleport the simulation to anywhere, right? And so what we're going to try and do is try to generate behavior, but without any of the pain of demonstrations or reward design. We're going to use resets to do so. And so the key idea that we're going to leverage is that resets can make exploration easier. So the hard part about reinforcement learning is often you're like exploring the world, you're trying random stuff, and you have to like, it's a needle in a haystack problem, right? So imagine your goal was in the green star, you started over on the left. Now you have to like try a bunch of random stuff until you like accidentally hit the goal, right? And that is a huge pain, takes a huge amount of compute, and that's often what you use the reward design to do, is to like direct the way you're switching. Right? And so if I'm always starting at the starting point, imagine I'm like wiggling my arm randomly, like I have to randomly chance upon the green star, and that is kind of a pain. But the idea behind using resets is that I don't have to start at the first point anymore. I can reset myself all the way to the last point, right? And then I'm solving a much easier problem. It's like, imagine I reset right next to the target. I'm solving a much easier problem. And then I reset one step away. And then I reset 2 steps away. And then I reset 3 steps away. Right? And so if I'm able to use the fact that I can teleport in my simulation, I can get behavior a lot more easily because I'm only solving easy, short horizon problems. And so the idea that my students, Patrick and Tyler, kind of took is that if you can reset really, really broadly in a simulation, so these are some of the examples of reset states. You can see there's like partial assemblies, partial grass, resetting the arm all over the place, right? If you can do that, then you can get your reinforcement learning to learn behaviors without any fancy reward design, with only sparse rewards, with no demonstrations, And you can generate these programmatically, right? So the idea is that you use the fact that you have privileged resets in simulation and you just reset all over the place. And then you run reinforcement learning starting from all of those places, right? And so let me skip through the next part maybe, but what results from this large-scale reinforcement learning, right, is this kind of behavior that you get without any demonstrations. This is not provided by a human. This is only with a sparse reward. And you can see that it has like lots of interesting non-prehensile adjustment behavior that you'd expect from a human, like rearrangement, wiggling, flipping, right? You can like do furniture assembly. You can see that it like lifts things over, uses the side of objects to do like non-prehensile interesting manipulation. But the cool thing is it's the exact same code for both tasks. The only thing you did is you provided them the CAD models, and it's exactly the same code, no reward design, no demonstrations, right? You can apply this across many, many, many tasks. It doesn't work for every single problem, but works for a large range of these contact-rich tasks and works from anywhere. Right? So if you're the lazy potato like me, you think about, okay, I don't want to collect more and more and more data, so is this thing really robust? And you can see that like if you had collected data, it's hard to see, but you can see a few green X's on this middle plot. Whereas if you do this like really broad reset, you get success anywhere. So you can place it anywhere and it'll assemble the table for you. Right? And so you can take this a step further and you can go and assemble a table with 4 legs, or you could do like other tasks like picking and placing and, you know, like I find the one on the bottom right really interesting because you're like trying to like rearrange this block against this table, but you can see that it like learns to use the environment in interesting ways. And so the cool part here is all of it is emergent, right? None of it is like hand coded. All of it is just emergent from large scale reinforcement learning. Okay, so the important takeaway here is that if you use the privileges of simulation, it allows for lots of cheap and robust data generation, but you have to be careful in how exactly you use that simulation, right? And so for my lazy potato though, it's taken me away from environment design, and now it's taken me away from reward design, right? So I'm way happier, I'm able to get behavior and simulation without the pain. Okay, and then the last section is around real world deployment, right? We're roboticists, we care about the real world, and we want robots to do things in the real world. And simulation is inherently wrong, right? So if simulation and reality were compared, they're inherently wrong, the physics is wrong, the visuals are a little wrong, and I could go in and I could adjust the sim and the sim to match reality more, I could identify things perfectly, right? But that makes me unhappy because I'm lazy. And so I could, of course, spend more time making simulation accurate, but what I'm going to do instead is I'm going to try and improve autonomously in the real world without putting in effort. So I'm going to try and say, can I run an algorithm autonomously in the real world to go from the behavior on the left, which is failing, to the behavior on the right, which is successful, without putting in lots of effort, right? And the important thing to think about here is what simulation is wrong, but it's still useful for certain things, right? So for instance, simulation is good at capturing the global strategy of a problem, right? If I have to pick up a leg and insert it and rotate it, it kind of captures that global structure just fine. What it sometimes struggles with is getting the exact physics a little bit wrong, right? So like if you're getting the forces a little bit wrong or the contacts a little bit wrong. And so what we're going to do is we're going to try and like cover global planning or like the global structure of the problem from simulation, and we're going to try and fix the local acting from the real world. So we're going to capture the big, long structure of the problem from sim and fix the little bits of detail from real data, right? I'm largely going to skip through the details here, but essentially we kind of use world models to do this, like you've seen a lot of these tools in the AI literature, like dynamics models or predictive models of the future. And so we're going to try and cast this as a world modeling problem, but we're going to try and freeze some of the long horizon parts of the problem from simulation and only adjust the short horizon prediction parts from the real world, right? And so the paradigm we're going to take is pre-train a world model in simulation and just adjust little parts of it in the real world, right? And since we're a little short on time, let's get straight to the results. But you can see what happens is that, you know, if you transfer things from simulation to reality at first, you see that it's not quite that wrong, but it gets a little bit of the details wrong, which makes it hard to like insert the leg properly. But if you adjust with little bits of real data autonomously, you can get like full furniture assembly that looks something like that, right? And so the point here is that I didn't have to put in any effort. The algorithm ran autonomously and fixed itself. You can do similar things for other tasks too. Again, all the tasks that you see were transferred directly and they don't work. But if you transfer them and adjust it a little bit, it gets a lot better. So like interesting things to see here is that it like learns how to like flip up the object and like do pretty interesting dynamic motions just by little bits of real world data. You can also apply this to like other problems like quadrupeds and so on. And the interesting thing is it like fixes those little physics mistakes, but it captures the general structure of walking pretty well from simulation. Okay, so the important part here is that we can make real world adaptation a lot easier through simulation. So simulation is not a silver bullet, but it can make real world adaptation super fast and super easy. So within 15 minutes of data collection. So, and the last bit is I don't have to go and fix my simulation and bridge this sim to real gap as a human. I just allow the data to do it. Right? And so the important thing here is that simulation can be a good way to scale up data for robotics, but it's all about managing costs, right? So managing costs and managing effort. And so you want to do that while representing the diversity of the real world. Right? And so that's going to make you or me as a lazy potato happy. That's really our goal in life. These are the papers we covered and the students who worked on it. Yeah, thanks for your attention.
Abishek, can you hear me?
Happy to take questions if any.
Thank you very much for the talk. And to anyone in the audience who has to go, you can go. But whoever has questions, we're happy to take them. So just raise a hand.
Thank you for the talk. Just a question on the resetting paper, where you leverage the fact that you're able to reset in simulation environments, but not in the real world. How do you define for different tasks? We saw one example where you're doing a construction, so you might, for example, have different parts of it already assembled. But have you thought about for other types of tasks how you define closeness for your problem, and how do you avoid when defining closeness a bias, let's say, towards learning a particular policy? Because of that inherent definition of closeness, or that's biased towards it.
Oh, you might have to repeat that for me because of the audio. I heard something about how do you define the reset state, but I like missed a bunch of the details. Sorry.
Let's use this mic.
Okay. Okay. Good. Yeah. All right. Thank you. Awesome. Sweet. Yeah, that's
okay.
Good.
We're gonna try again. Can you hear me now?
Okay.
Yes.
Yes, that's perfect. Yeah.
Great. So the question was just when it comes to resetting in a simulation environment, how do you define for different tasks what it means to be close to the end state? We saw one example there with constructing materials, but for other tasks, I can imagine that you might induce, depending on your definition, a bias towards your learning.
Yeah. No, that's a great question. So what we did is we applied it to some general class of assembly problems, right? So we want to like insert the drawer, assemble the leg, right? And so the way we did is we assumed that the user provides you what a full assembly looks like a complete assembly, and then we kind of went backwards from there. So you like start from the complete assembly, and then you start adding small amounts of noise to your policy, and that gets you to like near assembly states. I think a relatively general way of doing at least assembly problems is this assembly through disassembly paradigm. Like you take a fully assembled thing and then you start to disassemble it, and that gives you some nearby states. But I think it's a pretty open question how you do this for the broader class of any problem. It's a good question.
Cool. One more question there.
Hi, thank you for the talk. So for the real to sim part, you showed that you were collecting data from the real world and articulating it in simulation, which was very cool. I was wondering if you think that there would be a way to also capture the physical properties of those objects and trying to bring them into simulation.
Yeah. That's a great question. So we've tried this a couple of times, like figuring out the physical properties of friction or softness or damping or things like that. And so you can kind of poke around with the world and use that data to set the properties. What we found is that often it is less effective to do that than it is to just choose a reasonable range of parameters in simulation and just train a policy that's robust or adaptive to those parameters. So I think, at least in the tasks we've considered, which in the first part are not that dynamic, it hasn't made that big of a difference. But there's lots of interesting ways to do system identification of objects and physics parameters that you can try. But I think it's an open question on which problems does it make a big difference. Yeah, that's a good question.
Okay, thank you so much. What? Do you have time for one more question, or? Yeah?
Yeah, of course.
Okay.
Yeah.
Can we take the mic so the others here? Okay. We'll figure out the mic situation for next time.
Okay, so my question is for the reconstruction, actually, how do you guarantee that it's robust enough? Because I imagine you just do it with an iPhone, right? It has depth cameras and lidars inside of it, but with other phones, you probably can't do it yet. And also for the object detection and segmentation, how can you guarantee that it's actually correctly detects the affordances? It's kind of vague to me, honestly.
Yeah. It's an interesting question. From the iPhone, we don't actually use anything except for the camera images. So we don't actually use the depth, and we don't use the LiDAR and stuff. So I guess with these Gaussian splatting techniques, it's just from raw camera images, and use this technique called cold map to figure out where all the cameras